What if the real paradox of quantum physics isn't that particles behave strangely, but that your very act of looking is part of the experiment, whether you meant to join it or not? You can spend your whole life believing reality is something that happens out there, independent and steady, like a landscape that doesn't care who's walking through it. And then quantum physics arrives with its calm, unsettling suggestion. At the smallest scales, out there and in here aren't cleanly separated. The question isn't only what the world is doing, it's what the world becomes when you ask. Welcome back, traveler. Tonight we drift through science. You're in one specific place as you listen, maybe stretched out under a blanket, maybe on a couch with the lights low, maybe working late with headphones on, letting the room go quiet around you. If this kind of gentle, midnight science is your way of slowing the mind down, you can like the video, subscribe, and tell me where you're listening from and what time it is there, so the night feels a little less solitary and a little more shared. If you're here because sleep won't cooperate, you don't need to fight it. It's okay to be awake. It's okay to be tired. It's okay to want a story that doesn't demand performance from you. Tonight isn't a test, and you don't have to understand every detail to belong in this space. Let your attention loosen its grip. Let your thoughts wander and circle back. If you drift off halfway through a paradox, that's perfect. You're not here to memorize quantum mechanics. You're here to rest while your imagination quietly learns new shapes. So here's the map we'll follow, softly and slowly. We'll move through the famous quantum paradoxes, not as trivia, but as pressure points where our ordinary intuition fractures, superposition, measurement, entanglement, uncertainty, and the strange ways information behaves when you try to pin it down. And we'll always pair the big ideas with the human side of discovery. The labs with their dim indicator lights, the interferometers, the detectors that click like tiny metronomes, the researchers who argued for decades over what the equations mean, and the occasional hilarious mistake that turned into a breakthrough. This channel is for people who love big questions, but need a calm place to explore them at night. Here on Orbis Sleep, we like to hold science with two hands at once. One hand for precision, and one hand for wonder. We'll keep the language gentle, the images vivid, and the pace unhurried, because the goal isn't to solve quantum physics before bed. The goal is to let the strangeness become soothing, the way ocean waves are soothing even when you can't count every drop. So settle in. Adjust your pillow, let your shoulders sink, and if you want to close your eyes, go ahead. Tonight, we'll walk slowly into the smallest world we know and see why it refuses to give us a single, tidy explanation. In your mind, you can imagine a small, dark room where nothing looks dramatic at first. A table, a metal box, cables that snake like sleepy vines. Somewhere inside that box, a source releases single particles, photons, tiny packets of light, one at a time, not as a beam, but as solitary visitors. The air is still. The only sound is a soft hum from equipment and the faint click of a detector that seems too quiet to be describing the foundations of reality. Here's the first strange truth. Quantum physics doesn't begin with tiny things are tiny. It begins with the fact that tiny things behave like waves of possibility, not waves made of water, but waves that describe where something could be and what it could do. When you haven't measured the particle yet, the theory doesn't pick one definite story for you. It gives you a spread, a set of possibilities with different weights, like a calm fog over a landscape you can't quite see. This isn't just poetry. There's a concrete structure underneath it, called the wave function. You don't have to hold the math to understand the mood. The wave function is the universe's way of saying, here are the chances. When you measure, you don't reveal a hidden answer that was always there. You force the world to hand you a single outcome from that spread. That transition, possibility to actuality, is where the paradoxes love to live. One of the simplest ways to feel this is through interference. You've seen it with water ripples. Two waves overlap, and sometimes they reinforce each other, sometimes they cancel. Light does it too. In the famous double-slit experiment, Light passing through two slits can create an interference pattern, bright and dark bands on a screen. The pattern is a signature of wave behavior, as if the light goes through both slits at once and interferes with itself. The truly unsettling part comes when you send the light one photon at a time, not a stream, not a flood. Single photons, spaced out so they can't meet each other. And still, if you don't try to learn which slit each photon took, the interference pattern gradually appears. Each photon lands as a single dot on the screen, like a particle, but collectively, the dots build a wave-like pattern, as if each photon carried a private cloud of possibilities, and that cloud shaped where it could land. You can picture the human scene when this sinks in. Someone watches the screen accumulate faint points over hours. Someone checks the alignment. Someone worries about vibrations from a nearby elevator. Someone reruns the calibration because the dark bands look slightly too bright. No one in that lab is trying to be mystical. They're trying to be careful. And yet the careful result is something that doesn't fit the old intuition. A single particle behaving in a way that seems to require it to travel more than one path. Now comes the paradox lever. As soon as you install a which path detector, some device that can tell you which slit the photon went through, the interference disappears. The wave-like pattern collapses into something more ordinary, like two overlapping blobs. In other words, the mere availability of which path information changes the outcome, not because the photon is shy, because the experiment's setup defines what kinds of questions nature is allowed to answer consistently. This doesn't mean consciousness is magic. The observer in quantum mechanics is not necessarily a mind. It's any interaction that records information in a way that can't be undone. A detector, a scattering event, a mark left in the environment. The universe doesn't wait for you to notice. It changes when information becomes anchored, when the world keeps a receipt that says, "This happened." There's a quiet number that helps you feel how hard it is to keep the quantum fog intact. Even a single photon can have a wavelength of hundreds of nanometers, say around 500 nanometers for green light, while the devices that try to track it can disturb it at comparable scales. And for electrons, their de Broglie wavelength depends on momentum, meaning the waviness is tied to how gently you handle them. The more precisely you demand a path, the more you kick the system into a different kind of behavior. So the first paradox begins to form, not as a philosophical trap, but as a practical rule. You can have interference, or you can have which path knowledge, but you can't have both at full strength. It's not that the particle is hiding the truth, it's that truth is contextual here. The question you ask, wave-like or particle-like, requires a different experimental arrangement, and the universe answers the question you actually built, not the one you wish you could ask simultaneously. In the lab, this becomes a game of protecting fragile coherence. Scientists isolate systems from vibrations, from stray electromagnetic fields, from thermal noise. They cool atoms, trap ions, build interferometers, and try to keep the environment from quietly measuring the system for them. Because the environment is always trying to steal information, like a curious cat pawing at a closed door. And once information leaks, the quantum fog condenses into a single, classical-looking outcome. This is where the term decoherence slips into the story like a soft footstep. Decoherence doesn't solve the deepest riddle, but it explains why macroscopic objects don't look like quantum superpositions. The world is noisy. The environment entangles with everything. Phase relationships wash out. The interference that makes superposition visible becomes practically impossible to observe for large systems. It's not that superposition stops being true, it's that it becomes untrackable in practice, like trying to keep a single perfume molecule from mixing into the air, and yet humans have pushed the boundary. We've coaxed larger and larger systems into quantum states. Big molecules showing interference, superconducting circuits behaving like artificial atoms, mechanical resonators cooled toward their quantum ground state. These aren't thought experiments anymore. They're hardware. They're evidence that the quantum rules are not just for the microscopic, They're the underlying language of reality, with classical behavior emerging as a kind of statistical, information-leaking blur. If you let that sink in slowly, the paradox starts to feel less like a contradiction and more like a new grammar. Quantum physics isn't saying your nothing is real. It's saying reality has a different structure than your everyday narrative expects. Possibilities can be real in a mathematical sense. Outcomes can be real in a recorded sense, and the bridge between them, measurement, information, entanglement, is where your intuition trips, because it wants the world to have one story at all times. And if you're somehow still awake after watching a single photon, politely refuse to choose a single path until the universe starts keeping receipts, that's genuinely impressive. You might be exactly the kind of night brain this channel was built for. If you want more late-night science stories waiting here for you, you can subscribe. No pressure, just a tiny breadcrumb for your future self. There's a quiet assumption most of us grow up with, that measurement is passive. You look at something and it simply reveals what was already there. A thermometer doesn't change the temperature of the room in any meaningful way. A clock doesn't affect the time it displays. But in the quantum world, this assumption dissolves almost immediately. Measurement is not a window, it's an interaction, and interactions leave marks. Picture yourself in another lab, this one colder, dimmer, filled with stainless steel chambers and faint blue indicator lights. Inside, atoms are trapped and cooled until their motion slows to a whisper above absolute zero. At these temperatures, thermal noise quiets down enough that quantum effects don't get drowned out. What you're left with is not clarity, but sensitivity. Everything matters. Every interaction counts. In quantum mechanics, to measure is to couple a system to something else. A detector, a photon, an environment, and the moment that coupling happens, the system and the measuring device become entangled. Their states are no longer independent. They form a single description. This is where the old picture of the particle having properties starts to fail, because properties now belong to the combined system, not the particle alone. You can feel the tension here. Before measurement, the system is described by a wave function, a smooth, continuous spread of possibilities. After measurement, you see one definite outcome. Somewhere in between, the mathematics tells you to replace that smooth description with a sharper one. This step is often called collapse, and it's one of the most uncomfortable words in all of physics because it doesn't arise from the same equations that govern everything else. The Schrödinger equation, the core rule of quantum evolution, is gentle and deterministic. It smoothly evolves the wave function forward in time, no jumps, no drama. And yet, measurement seems to introduce a sudden update, a discontinuity. The theory itself doesn't explain when or why this happens. It simply tells you how to calculate probabilities, then instructs you to apply a different rule once an outcome is recorded. Physicists noticed this problem almost immediately. In the 1920s and 30s, the debates were intense, personal, sometimes bitter. Einstein famously objected, uncomfortable with a theory that seemed to depend on observation. God does not play dice, he said, not as a joke, but as a protest against indeterminacy. Bohr replied with patience and steel, insisting that physics was about what can be said about nature, not about nature in itself. This disagreement wasn't philosophical fluff. It was about operational meaning. When exactly does a quantum system stop being a superposition and start being a fact? Is it when a human looks? When a detector clicks? When information becomes irreversible? Or when the environment entangles with the system so deeply that interference becomes impossible to recover? You can imagine the human side of this confusion. Researchers staring at chalkboards late at night, pages filled with symbols, crossed out and rewritten, arguments carried out in letters, conferences, cafes. Everyone agrees on the predictions. Quantum mechanics works with absurd precision. Atomic clocks, semiconductors, lasers, MRI machines. And yet, beneath the success, the meaning remains unsettled. There's a useful idea here called information. In quantum physics, information is not abstract, it's physical. If information about a system leaks into the environment, even in principle, the system behaves differently. A scattered photon carries information. A vibrating molecule carries information. Once that information exists somewhere in the universe, the superposition becomes effectively inaccessible. This is why measurement doesn't require a conscious observer. A Geiger counter clicking in an empty room still measures. A cosmic ray ionizing air still measures. The universe is constantly measuring itself, not intentionally, but inevitably. Every interaction leaves traces. Every trace narrows possibilities. Reality doesn't wait to be watched. It waits to be entangled. There's a quiet number that helps anchor this idea. The Planck constant, about 6.2610 346.626 IMs 10 rho 6.62610 34 joules seconds, sets the scale at which these effects matter. It's tiny, almost absurdly so, but it's non-zero. And that non-zero value is what prevents you from measuring everything with infinite precision without consequence. It's the universe's way of saying, information has a cost. So the paradox sharpens. If quantum systems evolve smoothly, but measurement introduces abrupt outcomes, where exactly does the smooth story end and the sharp one begin? Is collapse real, or is it just an update to our knowledge? Different interpretations answer differently, and none of them are experimentally distinguishable so far. The math agrees, the stories diverge. Some interpretations say the wave function never collapses, others say it does, but according to rules we haven't fully discovered. Some say all outcomes happen, branching into parallel histories. Others say only one happens, chosen probabilistically. What's remarkable is that every one of these stories leads to the same experimental results. The paradox isn't in the data, it's in the explanation. And this is where the tone of quantum physics quietly changes. It stops being a theory about particles alone and becomes a theory about limits. Limits on knowledge, limits on description, limits on how cleanly reality can be divided into observer and observed. The paradox isn't a bug, it's a boundary marker, telling you where classical intuition runs out of road. If you let that idea rest gently instead of wrestling it, something soft happens. You don't need the universe to give you a single, final story tonight. It's enough to notice that reality is consistent, predictive, and deeply strange in ways that don't threaten you. The world isn't unstable, it's just subtler than your everyday language was designed for. And as this settles in, another question begins to form quietly underneath the first. If measurement reshapes reality by creating facts, what happens when two distant systems share information in a way that measurement can't easily separate? That's where the paradox becomes not just local, but deeply connected. Imagine two small detectors on opposite ends of a corridor of darkness. Maybe one is in a basement lab in Vienna, the other in a field outside the city, connected only by timing signals, fiber optics, and a shared agreement about what counts as now. The equipment is ordinary looking, metal housings, cables, blinking LEDs, but the question it asks is not ordinary at all. Can two separate things behave like one system, even when they are far apart? Entanglement begins like a promise the universe makes and then refuses to explain. When two particles interact in the right way, created together, scattered together, measured in relation to each other, they can share a single quantum description. Not particle A has a property and particle B has a property, but the pair has a property. Their outcomes become correlated in a way that can't be reduced to hidden notes tucked inside each particle. A simple example is polarization, the orientation of light's electric field. You can create pairs of photons whose polarizations are linked. If one is measured and found horizontal, the other will be found vertical, depending on how the pair was prepared. The eerie part is that before measurement, neither photon has a definite polarization on its own. The definite results appear when you measure. and yet the pattern of correlations appears as if they were coordinated from the start. This made Einstein deeply uncomfortable. In 1935, he and his colleagues Podolsky and Rosen wrote a paper, now called the EPR argument, suggesting quantum mechanics might be incomplete. Their intuition was classical. If two particles are far apart, what you do to one shouldn't instantly determine the state of the other. Einstein called it spooky action at a distance. He hoped the weirdness was just a sign that quantum theory was missing hidden variables, extra information that would restore a local, intuitive reality. For a while, this was a philosophical stalemate. Quantum mechanics predicted the correlations. A hidden variable theory could, in principle, mimic them. The debate felt like arguing about the meaning of a shadow without being allowed to touch the object casting it. Then, in 1964, John Bell did something quiet and brilliant. He derived a set of inequalities, Bell inequalities, that any local hidden variable theory must satisfy. Quantum mechanics predicted violations. That turned the argument into an experiment, and humans, of course, built the experiment. You can picture the work. Lasers aligned through crystals that split light into entangled pairs, optical tables floating on air to reduce vibration, polarizers rotated with precision, timing electronics synced so that detections can be matched pair by pair. Someone watching coincidence counts rise and fall as angles change, seeing the correlations trace a curve that no local hidden variable model can follow. The lab doesn't look like a temple of metaphysics. It looks like engineering, but the result feels like a door opening. In the 1970s and 80s, Alain Aspect and others performed increasingly refined tests. In the decades since, experiments have closed loopholes and pushed distances across cities, between mountaintops, even to satellites. The consistent outcome is that Bell inequalities are violated in exactly the way quantum mechanics predicts. The universe does not behave as if each particle carries pre-written local instructions that determine every possible measurement outcome in advance. Here is the paradox in its cleanest form. The world appears to be non-local in its correlations. Not non-local in the sense of sending signals faster than light, because entanglement can't be used to transmit controllable information instantaneously, but non-local in the sense that the joint system's description can't be decomposed into independent parts with local hidden properties. The pair is one story, even when separated. If you slow down and feel that, you'll notice it's not just spooky, it's a different ontology. It suggests that separateness is not fundamental, that what you call two objects might be a convenient label for a single quantum state spread across space. In a way, entanglement is the universe's reminder that reality is allowed to be relational. Not everything has to be a self-contained thing. There's an important safety rail here. Relativity still stands. No usable faster-than-light messages are hiding in entanglement. When you measure one photon, your outcome is random. You can't choose it. And the other side's outcome is random too, until you compare notes later and discover the correlations. The mystery is not, how do we send information instantly? The mystery is, how are the correlations there at all without a local script? To anchor it with a simple image, imagine two coins that are flipped in separate rooms. Each flip looks random. But when you later compare the results, they match perfectly, or match according to a rule depending on how you set your measurement angles. No classical mechanism can do this without either pre-agreement of outcomes for every possible measurement setting or a hidden influence traveling between rooms. Bell's theorem says, if you insist on strict locality and pre-existing properties, you can't get the quantum statistics. At this point, you might expect the paradox to demand a choice. Either reality is non-local, or outcomes aren't determined until measurement, or many outcomes happen in branching histories, or the wave function is a kind of information rather than a physical object. Different interpretations take different exits. But the experiment doesn't tell you which philosophical exit is right. It tells you the building is real, the stairwell exists, and your old map of the halls was incomplete. The human side of entanglement is also strangely tender. Researchers spend years trying to remove every mundane explanation. They worry about detector efficiency, about timing windows, about settings that might not be truly random, about subtle channels of communication. They build random number generators based on quantum noise or distant cosmic photons. They design loophole-free tests. It's meticulous, almost obsessive care. And out of that care emerges a result that feels like poetry. Reality does not break into independent pieces as cleanly as you wanted. This is why quantum paradoxes are so hard to explain away. They aren't just counterintuitive, they're structurally different from classical thinking. Classical physics assumes the world is made of parts with properties. Quantum physics says, sometimes the world is made of correlations first, and parts are secondary. The paradox is your intuition insisting on separateness in a place where separateness is optional. If you let that settle gently, entanglement starts to feel less like horror and more like connectedness. An austere kind, not emotional but mathematical. The universe is not lonely at the foundations, it's linked, it's relational. And your own ordinary sense of a separated self might be, at least in the deepest physics, a useful approximation rather than a fundamental truth. And now there's a quieter twist waiting behind the curtains. If entanglement ties distant things together, and measurement seems to create facts, what happens when you combine both ideas in a single setup, where you can choose, after the fact, what kind of history the particle should have had? That's where the paradox starts to play with time itself, and the story gets even stranger. You can imagine it like this. The universe is patient, and your mind is the one that rushes. Your mind wants to ask, which path did it take? And when did it decide? As if nature is obligated to write a single timeline in ink. But quantum experiments sometimes behave as if the timeline is written in pencil until information hardens it. Not because reality is indecisive in a human way, because the kind of story you're allowed to tell depends on what information exists and what information is erased. A photon leaves a source, and you picture it traveling like a tiny marble, clean trajectory, a straight line. But then you remember the double slit, the interference, the way single dots accumulate into a pattern when which path information is unavailable. The photon lands as one dot, particle-like, yet its distribution speaks wave. Your intuition wants to say, okay, fine, it went through both. And the physics replies gently. The question through which slit is not a question with an answer, unless the world keeps a record. Now take that fragility and place it inside a choice made late. In delayed choice experiments, you set up a system where a photon's behavior can look wave-like or particle-like, depending on the measurement configuration. The unsettling part is that the choice of configuration can be made after the photon has already entered the apparatus, sometimes after it would have had to decide which story to follow if it were a classical object with a classical history. John Wheeler, one of the great architects of 20th century physics, loved this thought experiment because it forces you to feel your assumptions. He described versions where light from a distant quasar, billions of years away, passes by a galaxy that acts like a gravitational lens, splitting the light into two possible paths that later recombine. In principle, you could decide at the last moment whether to observe interference, as if both paths were taken, or which path information, as if only one was taken. Your mind immediately panics and tries to assign blame to the past. In the laboratory, the distances are smaller, but the logic is the same. A beam splitter can act like a fork in the road, creating two paths. Another beam splitter later can recombine those paths so they interfere. If the recombining device is present, you see interference, wave-like behavior. If it's absent, you get which path information, particle-like behavior. The paradox is that the decision about whether recombination happens can be made after the photon has already passed the first beam splitter. It's tempting to describe this as the present changing the past. But notice what's actually being changed, not the raw events, but the type of description that remains consistent. Quantum mechanics doesn't say the photon really traveled as a wave and then later changed its mind into a particle. It says the photon plus apparatus system is described by a quantum state, and your measurement defines which complementary aspect becomes definite. The past you imagine is not a recorded fact, it's a story you're trying to tell. This becomes even more vivid in the quantum eraser. You can set up an experiment where which path information is, in principle, available, meaning interference disappears. But then you manipulate the system so that the which path information is erased and interference can be recovered in the correlated data. It feels like you are undoing knowledge. And in a sense, you are making it so that there is no longer any physical record distinguishing the paths, even in principle. A classic version uses entangled photon pairs. One photon, the signal, goes toward a screen where you look for an interference pattern. Its entangled partner, the idler, goes through a setup that either preserves which path information or erases it. When you look at the signal data alone, you don't see a clean interference pattern. But when you sort the signal detections based on how the idler was measured, based on which subset of events corresponds to erased information, interference appears in that subset. There's something soothing hidden in this once you stop fighting it. It means no paradoxical message is being sent backward in time. The signal photon's local statistics remain bland, as they must. No controllable faster-than-light communication, no magical retrocausality you can exploit. The strangeness appears only when you compare correlated data. The interference isn't turned on the screen by a future choice. It's revealed in the relationship between two sets of outcomes, once you decide how to group them. You can picture the human scene again, long nights collecting counts, aligning optics, checking coincidences within tight timing windows. Modern experiments can register detections on nanosecond timescales, matching pairs across separated detectors with exquisite precision. People argue over whether a delayed choice was truly delayed relative to the relevant events, so they add fast random switches and long fiber loops. The paradox survives the engineering improvements. It isn't a loophole, it's the structure. What makes it feel like time is being toyed with is that your brain insists every particle must have had a single definite past. Quantum mechanics resists that insistence. It offers a subtler claim. Some past tense questions are not meaningful unless the world has retained the distinguishing information. If there is no physical record, the demand for a single narrative is not a demand the universe has to satisfy. You are asking for a story the evidence cannot support, because the evidence was never created. This is why observer is such a misleading word. It makes you imagine a person staring like reality is shy. The real character here is information. When which path information exists in the environment in an irreversible way, interference fades. When that information is erased, when the environment has no receipt that says it went this way, the wave-like correlations can show up again. It's less about human awareness and more about whether the universe could, even in principle, distinguish alternatives. If you keep this gentle, you can almost feel the paradox relaxing. The universe is not contradicting itself. It's refusing to let you combine incompatible descriptions into one classical movie reel. Wave-like and particle-like are not two costumes the photon changes into depending on your mood. They are two different experimental questions, and each question has a consistent answer in its own context. The discomfort comes from trying to force both answers into a single, uninterrupted storyline. Some people try to escape by saying, "Oh, fine, everything is decided, we just don't know." But Bell's theorem already made that escape narrow. Others say, "Fine, everything happens, branching." That escape is wide but emotionally expensive. Others say, "Fine, the wave function is knowledge, not reality." That escape is tidy but raises new questions about what knowledge is about. Every interpretation is a way of choosing what you're willing to sacrifice: locality, uniqueness, realism, or classical storytelling. Here's a calmer way to hold it for tonight. Quantum physics is a set of rules for what can be predicted about outcomes when you interact with systems at small scales. It is incredibly good at that job. The paradoxes appear when you demand it also provide a classical-style account of what was happening between interactions, as if nature must maintain a hidden diary written in ordinary language. Maybe the diary exists in a language we don't speak yet, or maybe the demand itself is the mistake. And still, despite all this strangeness, your world remains stable. Your phone works because quantum tunneling and band structure behave reliably. Lasers behave, transistors behave, timekeeping behaves. Quantum mechanics is not chaotic in practice, it's precise beyond anything classical physics ever offered at the smallest scales. The paradox is not unreliability. The paradox is the mismatch between precision in prediction and ambiguity in narrative. So if you're lying there, letting the room stay dark, you can take a slow breath and let that be enough. Let the universe keep its secrets without feeling like it's mocking you. Let the paradox feel like a soft edge, not a threat, like the shoreline where the ocean is deep, not broken. And if information is the key to what becomes real, then one last question hangs quietly in the air. When you become part of the record, when your own memory is the receipt, what does that do to reality's story? There's a particular kind of quiet dread that shows up when quantum physics starts talking about facts. Not moral facts or social facts, physical facts, the kind you imagine as locked in place, like a footprint in wet cement. A detector clicked. A particle was found here, not there. A number was written down. In ordinary life, once a fact is recorded, it becomes part of the world's furniture. But quantum theory asks a softer, stranger question. A fact for whom, and at what level of description? Picture a small laboratory inside a larger laboratory, like a box within a room. Inside the inner lab is a scientist, Wigner's friend, performing a measurement on a quantum system. Maybe it's a photon's polarization, maybe it's an atom's spin. The friend watches the detector, sees a definite outcome, and writes it down. From the friend's perspective, something has happened. A possibility has become a result. The world, inside the lab, feels classical again. Now, step back outside the inner lab. You are Wigner, in the hallway with no access to the friend's notebook yet. From your perspective, if you treat everything, including the friend, the detector, the notebook, as a physical system, quantum mechanics suggests you can describe the entire inner lab as a superposition of different outcomes. Not because the friend feels blurry, not because the notebook is ghostly, but because, in principle, the wave function describing the full system evolves smoothly unless you interact with it. Here is the paradox, resting in your hands like something fragile. The friend says the outcome is definite. Wigner's description says the outcome is not definite relative to him until he opens the lab and becomes entangled with its record. Two observers, two descriptions, both derived from the same theory. Both apparently valid, and yet they can't both be the whole story in the classical sense. It helps to slow down and notice what quantum mechanics is really doing. It is not giving you the state of reality as a single absolute object. It is giving you a state description relative to a boundary, relative to what is included in the system and what is treated as an observer, an environment, a measurement device. The state is not just about the particle. It is about the cut you draw between what is being described and what is doing the describing. This is why the measurement problem refuses to stay in one room. You can push the boundary outward. If the detector measured the particle, maybe the detector is quantum too. If the detector is quantum, maybe the entire lab is quantum. If the lab is quantum, maybe the friend is quantum. If the friend is quantum, then where does definiteness enter? At what point does one outcome become a universal fact rather than a local perspective? Humans tried to make this discomfort concrete. Thought experiments became sharper. Variations multiplied. Some modern proposals, like the Frottiger-Renner argument, take the logic seriously and show that certain combinations of assumptions about single outcomes the universal validity of quantum mechanics, and consistent reasoning among observers can't all be true at once. It's like discovering a hidden triangle in your worldview where the angles refuse to add up the way you expected. You can imagine the practical side, too. Physicists trying to test observer layers with real devices, not with human friends in boxes, but with quantum systems that play the role of observers. Small quantum memories, qubits that store measurement results, interference experiments that attempt to reverse measurement-like processes. The dream is to see whether you can treat recorded facts as reversible at small scales, the way you can reverse certain quantum interactions if the environment hasn't stolen the information. This is where decoherence returns like a familiar tide. In everyday reality, records are not clean quantum states you can reverse. They are messy, amplified, copied into the environment. Heat, vibration, photons scattering off paper, air molecules colliding with ink. That copying process makes facts feel absolute. It's not that a wave function can't be written for the whole universe. It's that recovering the delicate phase information needed to reveal interference between macroscopic alternatives becomes unimaginably difficult. Still, the paradox matters because it points to something fundamental. The theory's success doesn't come with a single, universally agreed-upon story of what is real at all levels. You can calculate what happens with astonishing accuracy, but when you ask for a single picture of how facts emerge, you encounter a gap between the formalism and the narrative. The equations don't hand you a comfortable definition of objectivity the way classical physics does. Some interpretations respond by making collapse real, an actual physical event, not just a bookkeeping update. Others respond by denying collapse entirely, saying the wave function always evolves smoothly, and what you call an outcome is just one branch you experience. Others respond by saying quantum states represent information, not physical reality. So different observers can assign different states without contradiction. Each approach buys peace by paying a price somewhere else. You can feel the emotional shape of this, even if you don't chase the full math. Quantum paradoxes don't just say the world is weird. They say, your idea of a single, universal perspective might be optional. That's a deep challenge, because your brain is built around a single viewpoint. You live inside one stream of experience. You want the universe to honor that structure at every scale. Quantum theory whispers that, at the foundations, reality might be more relational than singular. But notice something gentle. This doesn't make your life unstable. It doesn't make your memories unreliable. It doesn't mean you vanish when you aren't observed. What it means is that the deepest layer of physics may not be naturally described in the language of everyday objects with absolute properties. It's described in relationships, correlations, and the flow of information between systems. Your ordinary world emerges when those relationships become irreversible and widely shared. If you're listening in the dark, you can let fact become a softer word tonight. Not a threat, not a riddle you must solve, just a sign that the universe has levels. At the surface level, facts are solid enough to build bridges and send messages and keep promises. Deeper down, facts may be local to an interaction, like a note exchanged between two systems, meaningful and real within that exchange. And this sets the stage for a particularly sharp paradox that seems almost cruel in its simplicity. If measurement creates facts, and facts can be relative to observers, what happens when you try to trap a system in a state where the absence of change is itself a kind of measurement? Where simply checking too often prevents motion from happening at all, that's where the quantum world starts to feel like it can freeze time, not by magic, but by attention. The phrase, "a watched pot never boils," feels like superstition until you realize quantum mechanics has its own version of it, except the pot actually refuses to boil for mathematical reasons. You picture a small system poised to change, an excited atom ready to emit light, a spin ready to flip, a fragile superposition ready to drift into a different state. In classical physics, time carries it forward, no matter what you do. In the quantum world, Your repeated checking becomes part of the dynamics, settle into the image of a single atom held nearly motionless in an electromagnetic trap. The room is quiet except for the lowest constant hum of electronics. A laser is tuned with almost absurd care. Someone watches a display that doesn't show a thing exactly. It shows counts, clicks, timing histograms. The atom is prepared in a specific state, and the question is simple. If left alone, it will slowly evolve away from that state. But what if you keep asking over and over, are you still there? Quantum mechanics says that at very short times, the probability of a system staying in its initial state doesn't decay linearly. It has a curved, quadratic start, like a gentle dip rather than a steep slide. That little mathematical curve matters. Because if you measure the system repeatedly, you keep resetting the question. You force the system back into still here or not here, and when the intervals are short enough, the most likely answer is still here. You don't stop time. You interrupt the system's ability to drift away. It helps to feel what measure means in this context. It isn't necessarily a human peaking, dramatic and conscious. It's any interaction that extracts information about whether the system is in a particular state. A pulse of light that would scatter differently depending on the state. A coupling to a detector. A correlation written into the environment. Each measurement pins the system to a basis, asking it to be definite in one specific way, again and again, before it has time to blur into alternatives. You can imagine it like tapping a swinging pendulum, except the tap is not a push, it's a question. In classical intuition, questions don't affect motion. Here, the question is an interaction, and interactions reshape the state. Are you still excited? Becomes a physical event. Are you still pointing up? Becomes a pulse that leaves a trace. The world is not passively observed. It is constantly negotiated through contact. The name Zeno comes from an ancient philosopher who loved paradoxes about motion, arrows that never arrive, steps that never finish. Quantum physics borrows the name with a small smile because the effect echoes that old tension. If you divide time into enough slices, something that should change can be prevented from changing, not forever in practice, but long enough to be measured. Long enough to feel the unease in your chest, like the universe is playing by rules your language wasn't built for. This isn't only theory. In the 1990s, experiments with trapped ions demonstrated versions of the quantum Zeno effect by repeatedly probing whether a transition had occurred. One famous setup used beryllium ions held in a trap, driven to evolve between states while frequent checks suppressed the transition. The lab work looks almost gentle. Pulses, timings, careful statistics. But the meaning is sharp. Measurement doesn't merely reveal reality. It can control what reality is allowed to become, and the numbers can be surprisingly concrete. Atomic transition times can be on the scale of nanoseconds to milliseconds depending on the system. If the natural timescale of evolution is say, a few microseconds, and you probe it every fraction of a microsecond, the evolution can be dramatically slowed. You can almost hear the rhythm of it. Pulse, silence, like a soft metronome keeping the system from wandering too far from home. In the quietest telling, the quantum Zeno effect is less mystical than it sounds. It's a consequence of how probability behaves in quantum theory at short times, and of how measurement projects a state. But it still feels like a paradox, because it violates a deep, everyday expectation that attention is passive, that observation is harmless. Quantum mechanics asks you to accept that information is physical, and physical acts have consequences, even when the act is just checking. There's another subtlety hiding here, one that makes the story richer. Measurement doesn't always freeze. Under some conditions, repeated interactions can speed up decay or transitions. This is sometimes called the anti-Zeno effect. It depends on the system's coupling to its environment and the timing of the interactions, like nudging a candle flame so it either steadies or flickers out faster. The same checking can become either a brake or an accelerator, depending on how it's done. You can feel the human side in the way researchers learn to think like engineers of possibility. They don't just ask, what does quantum mechanics mean? They ask, what can we make it do? The Zeno effect becomes a tool, useful for protecting quantum states in quantum computing, where unwanted interactions cause errors. If you can keep a fragile qubit from drifting into noise, you can hold coherence longer. In this sense, paradox becomes technology, but the deeper question doesn't go away. If measurements can freeze evolution, then the line between natural change and forced outcome becomes blurry. A system isn't simply evolving and then being read, it's evolving under a continuous background of interactions that decide what counts as stable. The universe, at small scales, doesn't have the luxury of being left alone. Everything touches everything, even gently. Everything leaves fingerprints. Think about how this circles back to your own night. You're lying there, and your mind keeps checking. Am I sleeping yet? Is it working yet? Why am I still awake? Those checks can keep the mind from drifting the way it wants to. The analogy isn't perfect, brains aren't qubits, but there's a strangely comforting resonance. Sometimes the most effective way to let change happen is to stop interrogating it. To stop demanding a definite outcome every few seconds. And yet, in quantum physics, you can't always stop the interrogation because the environment is always asking questions for you. Thermal photons, stray fields, vibrating atoms in nearby surfaces, each one is a kind of measurement. Decoherence is the universe's background noise of curiosity. It doesn't mean someone is watching. It means the world is interactive. And those interactions can either wash quantum strangeness away, or sat in the right experimental designs, hold it delicately in place. So you end up with a paradox that feels almost intimate. Measurement creates facts, and too many facts can prevent motion. A system can be trapped by certainty. Change can be suppressed by repeated confirmation. The universe begins to look less like a machine ticking forward regardless of questions, and more like a landscape where the questions themselves are physical pathways that redirect what happens. And now, with that in your hands, a sharper puzzle quietly appears. If frequent measurement can stop a quantum transition, what happens to processes that feel inherently spontaneous, like radioactive decay or quantum tunneling, things that seem to just happen without permission, and yet might still be slowed, sped up, or reshaped simply by how the universe keeps track of them? There are moments in physics where the word impossible quietly loses its authority, not in the loud, cinematic way, no thunder, no portals, just in the calm math of probability. Quantum tunneling is one of those moments. It tells you that a particle can appear on the other side of a barrier without having the energy to climb over it in the classical sense. If you try to picture it as a tiny ball, it feels like cheating. But if you picture it as a spread of possibility, it starts to feel like something the universe can do without breaking its own rules. Imagine a barrier as a hill you can't quite see in the dark. On one side, a particle is trapped. On the other side, it's free. Classical intuition says the particle stays put unless it gains enough energy to climb the hill. Quantum mechanics says the particle's wave function extends into the barrier, fading as it goes, like light dimming in fog. And if the barrier is thin enough, the wave function can leak through to the other side. When you measure, you might find the particle there, not because it found a secret tunnel in the soil, but because its possibility never fully stopped at the wall. The paradox comes from the way we speak. We say we're tunneled, as if it took a path. But the quantum description doesn't require a little traveler with a suitcase. It requires only that the probability amplitude exists on both sides. The barrier doesn't forbid existence, it suppresses it. The particle doesn't need a classical trajectory through the wall. It needs a non-zero chance of being found beyond it. The universe allows that chance quietly, and then occasionally cashes it in. This is not rare in the world that built you. Tunneling is part of how the sun shines. In stellar cores, hydrogen nuclei repel each other electrically, and classically, They shouldn't get close enough to fuse at the temperatures we actually have. But quantum tunneling gives them a small probability to slip through the Coulomb barrier and fuse anyway. That small probability, multiplied by immense numbers of particles, becomes a steady glow that warms oceans and skin and the quiet rooms where you lie listening. Tunneling also lives inside your devices. In a scanning, tunneling microscope, electrons tunnel between a sharp tip and a surface E, creating a current exquisitely sensitive to distance. Move the tip by a fraction of a nanometer, and the tunneling current changes dramatically, so dramatically that the microscope can map individual atoms. Again, no magic. Just the gentle fact that being forbidden in quantum mechanics often means being exponentially unlikely, not being impossible. Now place tunneling next to radioactive decay, and the paradox becomes even more personal. Radioactive decay feels like the purest kind of spontaneity. A nucleus sits there, identical to itself, and then, without warning, it emits a particle or splits. You can predict the decay rate of a large sample with stunning accuracy, but you cannot predict which individual nucleus will decay at which exact moment. Not because of ignorance, but because the theory itself gives you probability as the deepest level of description. This probabilistic law is so stable that we build clocks and dating methods out of it. Half-life is one of the most calming numbers in physics. The time it takes for half a sample to decay is reliably characteristic of the isotope. Carbon-14 has a half-life of about 5,630 years, which lets us date ancient bones and wood. Uranium-238 has a half-life of about 4.5 billion years, which is comparable to the age of Earth. These aren't vague patterns. They are consistent, measurable rhythms in the long breath of time. But for a single atom, the decay moment feels like a coin flip with no visible hand. The nucleus doesn't gradually wear down the way a battery does. It doesn't announce its intention. It just sits in a quantum state with a certain probability per unit time to tunnel through an energy barrier and decay. That barrier is not a physical wall you could tap. It's an energy landscape created by nuclear forces. The decay is, in a deep sense, tunneling. The wave function of the system leaks into a region corresponding to decay products. If you want a human-scale image, think of it like a sealed room where a scent is trapped. In classical thinking, the scent stays trapped unless there's an open door. In quantum thinking, the scent is a probability cloud that can seep through walls in a way that is not allowed in classical geometry. The walls don't stop it absolutely, they reduce it, and once in a while, a molecule appears on the other side. For a nucleus, once in a while is governed by an exponential law that becomes a half-life. The paradox becomes sharper when you remember measurement. If a decay is a probabilistic process, can you watch it and change it? In certain idealized treatments, frequent measurements can modify decay rates, linking this back to the quantum Zeno and anti-Zeno effects. In practice, it's complicated, because watching decay means interacting with the system in a way that creates records. Still, the idea is unsettling. Even spontaneous events can be influenced by the information flow between system and environment, and underneath all of it is the same tension you've been holding since the beginning. Quantum mechanics gives you a smooth evolution of a wave function, and then a sudden fact when an outcome is registered. Decay is a perfect stage for that tension, because it's a moment when something qualitatively different appears. A particle emitted, a nucleus transformed, energy released. Before, there is a superposition of undecayed and decayed possibilities in the formal description. After, there is a record, a click, a track in a detector, a bit of ionization in air. The universe keeps the receipt. The lab scenes here are both mundane and beautiful. Cloud chambers where invisible radiation becomes visible, trails like thin white threads, Geiger counters clicking in slow, irregular rhythms that feel like rain on a roof, detector arrays in underground mines, built to avoid cosmic noise, waiting for rare events. People calibrate, subtract background, argue over statistical significance, clean their data pipelines with the same tenderness you'd use to clean a lens. The paradox isn't in the mess. The paradox is in the cleanliness of the prediction and the randomness of the individual event. If you listen gently enough, decay starts to sound like a lullaby the universe sings without knowing it's singing. A steady law for the crowd, a surprise for the individual, predictable and unpredictable at the same time without contradiction. The paradox only appears if you demand that individual outcomes must be determined in advance by hidden causes you could, in principle, uncover. Quantum physics offers a different kind of order, probabilistic order, deep and stable. Not because it hides certainty, but because certainty is not the currency it uses at the smallest scales. And this is where another classic paradox waits, like a door you didn't notice. If a quantum event can be undecided until measurement, what happens when the undecided event is linked to something macroscopic, something that, in your everyday world, cannot be half true? Something like a cat, a vial, a click, a life or death outcome. That's where the paradox stops being abstract and becomes a story your nervous system recognizes immediately. Schrödinger didn't put a cat in a box because he hated cats. He did it because he hated the way the quantum story was being told. He wanted to expose a fracture in the narrative. If you take the equation seriously and you treat measurement as something special without saying exactly why, you can end up with a world where everyday objects must be described as superpositions. His cat was a spotlight aimed at the absurdity of applying the same quantum language to the microscopic and the macroscopic, without explaining how one outcome arrives. So picture the box, not as cruelty, but as a thought experiment with props. Inside is a radioactive atom with a 50% chance to decay in an hour. The atom is connected to a Geiger counter. The Geiger counter is connected to a mechanism that, if triggered, releases poison. The fate of the cat is tied to a quantum event. If the atom decays, the cat dies. If it does not, the cat lives. The paradox is not the cat. The paradox is the phrase you are forced to say if you treat the whole apparatus as one quantum system. Until someone opens the box, the cat is in a superposition of alive and dead. Your brain rebels because it knows what alive means. It knows what dead means. These are not states that can smear gently into each other the way polarization angles can. Macroscopic reality feels sharp. The cat either purrs or it doesn't. The air either carries warmth or it doesn't. The box either contains motion or silence. You can't hold half alive in your hands without turning it into metaphor. And Schrödinger's point was that this discomfort isn't just emotional. It's a logical pressure on the interpretation. In the formalism, the atom's wave function evolves into a superposition, decayed and not decayed. That superposition becomes entangled with the detector, clicked and not clicked, then entangled with the mechanism, triggered and not triggered, then entangled with the cat, dead and alive. In the clean mathematical language, the whole system becomes a single entangled state. And if you don't insert collapse somewhere, you seem committed to the idea that the cat is not in a definite condition until observation. But here's the calm part. In the real world, macroscopic systems are never isolated. They are bathed in interactions. The cat is a furnace of biochemical processes. Photons scatter off fur. Air molecules collide. Heat flows. Every interaction with the environment is a kind of measurement, a leakage of information that makes certain alternatives distinguishable. This is where decoherence enters, not as a philosophical escape hatch, but as an actual physical mechanism that explains why macroscopic superpositions become effectively unobservable. Decoherence doesn't pick an outcome the way collapse does. What it does is destroy the interference between alternatives. It scrambles the relative phases of the superposed components into the environment so thoroughly that you can't recombine them and see wave-like behavior at the macroscopic scale. The alive and dead branches become non-interfering. They evolve as if separate. From the outside, you no longer have access to the delicate coherence that would make alive plus dead behave like a single quantum wave. If that feels abstract, imagine writing a message in sand and then letting wind blow across it. The message still exists in the sense that the sand grains are still somewhere, but the coherent structure, the readable pattern, is gone. Decoherence is like that, but far faster and more thorough. For large objects, the timescales can be unbelievably short. A dust grain in air can decohere in a tiny fraction of a second. A swarm cat in a box doesn't stand a chance. So why does the paradox remain? Because even with decoherence, you still face the question, if the branches don't interfere, do they both exist? Or does one become real and the other vanish? Decoherence explains why you don't see superpositions in everyday life, but it doesn't fully explain why you experience a single outcome rather than a mixture of possibilities. It shows you how the world becomes classical looking, but not necessarily why it becomes single-threaded. This is where interpretations diverge again. In many worlds, the cat is both alive and dead in different branches, and you experience one branch because you are part of it. In collapse theories, the superposition physically collapses when systems become massive or complex enough, so only one outcome becomes real. In relational or cubist-like views, the cat state is not an absolute object. It is a description relative to an observer's information. Each approach tries to give you a consistent story without contradicting the calculations. There's also a detail often missed in casual retellings. Schrödinger didn't mean the cat is literally in a mystical limbo. He meant the interpretation that forces you to say that is suspicious. The cat is a mirror held up to your language. It asks, are you confusing the mathematical tool, the wave function, with a literal physical substance? Are you forgetting that the wave function is a recipe for probabilities of outcomes, not necessarily a photograph of what is between measurements? And yet experiments have pushed the boundary between microscopic and macroscopic further and further. Physicists have created superpositions of larger and larger systems, currents flowing in two directions in superconducting loops, molecules with thousands of atoms in interference experiments, mechanical resonators cooled near their quantum ground states. These aren't cats, but they are reminders that the classical world is not a separate kingdom. It's an emergent behavior that arises from quantum rules under decoherence. This is why quantum paradoxes are so hard to dismiss. They are not just quirks of tiny particles. They are hints that your everyday certainty is a surface phenomenon, stable, reliable, and real in practice, but built on deeper rules that do not care about your preference for single narratives. The cat is a warning sign posted at the boundary. Careful, your intuitions are changing states here. If you let yourself hold that boundary gently, you can feel the emotional progression shift. Earlier, the paradoxes felt like they lived out there, among photons and lab benches. Now the paradox touches the structure of experience itself. It asks why you see one world. It asks why facts feel objective. It asks why your life is not a blur of alternate histories. And the quiet answer offered by physics, so far, is because interactions spread information so quickly that the world becomes effectively classical, and because whatever selects outcomes, it selects them in a way that keeps your experience coherent. And still, a final twist waits with a kind of cold elegance. What if the problem isn't cats at all, but the notion that there is a wave function of the universe that needs interpretation? What if the paradox is a sign that our most successful description is also incomplete, not in predictions but in meaning? That question doesn't scream, it just lingers, like a dim star you can't stop looking at once you've noticed it. Sleep in your body for a moment, even if your mind is still curious. Let the room stay exactly as it is, blanket heavy, air quiet, that faint city hush behind the walls. Because what we're about to touch isn't loud, it's subtle. It's the kind of paradox that arrives like a soft receipt slid across a table, a set of numbers that say, with calm certainty, your old picture can't be the whole picture. Entanglement begins as a simple idea. Two particles can share a single quantum state in a way that makes their properties linked, even when they are far apart. You don't have to imagine a secret cable between them. You only have to accept that the best description of the pair is not particle A has this, particle B has that, but the pair has a pattern. When you measure one, you don't send a signal. You reveal which side of the pattern you're standing on. The shock comes from how strong the pattern can be. If you create pairs with correlated spins or polarizations and then measure them at different settings, the outcomes line up more tightly than any classical story with local hidden instructions can allow. It's not that the outcomes always match, it's that the statistical structure, the way matches and mismatches depend on your chosen angles, follows quantum predictions with uncomfortable precision. John Bell turned this discomfort into a test. He didn't argue about interpretation in circles. He asked a clean question. If the world is local in the classical sense, and if measurement reveals pre-existing values carried by particles like sealed envelopes, then certain inequalities must hold. Those inequalities are not philosophical preferences. They are mathematical boundaries for any theory that keeps both locality and realism in the classical way. Quantum mechanics predicts violations of Bell inequalities for entangled systems, and experiments, again and again, have seen those violations. In the 1980s, Alain Aspect's experiments with entangled photons helped solidify the phenomenon by changing measurement settings rapidly, reducing the chance that some slower conspiracy could coordinate the outcomes. The setups looked delicate. Optical tables, crystals, detectors, timing electronics, all insisting on a kind of honesty in nature. Over the decades, the tests became stricter. Researchers chased loopholes like people chasing drafts in a quiet old house. They tried to ensure that measurement choices were genuinely unpredictable and that information couldn't travel between detectors at or below light speed in time to coordinate results. They tried to avoid detection loopholes, where missing data might bias the sample. Eventually, while loophole-free Bell tests were performed using photons, atoms, and other systems, each experiment saying, in its own calm way, the universe is not playing by local hidden rules. Some of these experiments separate detectors by substantial distances, hundreds of meters now, even kilometers, and synchronize choices and detections with tight timing windows. You can picture it. Two stations blinking in the night, each making a random choice of measurement basis, each recording clicks, both later compared in a quiet room with coffee and code. The stations never whisper to each other in time, and still, the correlations show up indifferent to the distance. If you ask, so what is actually happening, you meet the paradox in its cleanest form. Either you abandon locality in the naive classical sense, or you abandon the idea that measurement outcomes were pre-written properties waiting to be revealed, or you abandon the notion that there is a single, observer-independent set of facts about all possible measurements at once. Bell's theorem doesn't tell you which sacrifice to make. It only tells you that you can't keep them all. This is where language gets you in trouble again. People hear non-local and imagine faster-than-light messages. But entanglement does not let you send information faster than light in any controllable way. The statistics at one location, by themselves, remain random. The paradox appears only when you bring the records together and compare them. It's as if the universe refuses to commit to a classical story for each particle individually, yet still maintains a strict, lawful pattern across the pair. You can hold that pattern like a constellation. The stars are separate points, but the shape lives in the relationship between them. If you stare at one star alone, it doesn't tell you the picture. The picture emerges when you see the whole sky. Entanglement is not a wire. It's a structure, a shared shape that becomes visible only when two measurements are seen as one combined event. Some researchers have tried to push the unease even further by making the random choice come from cosmic sources, distant starlight, so that the decision of measurement settings is linked to events that began long before the experiment was built. The idea isn't to prove the universe is spooky. The idea is to make it harder for any local hidden variable story to claim the settings were secretly coordinated with the particles, You start to feel how desperate classical intuition becomes when it tries to cling to its old comforts. And then there's the human response. Interpretations bloom like different ways of coping with the same night sky. Many worlds says the correlations arise because all outcomes occur, and the structure of branching preserves the pattern. Bohmian mechanics keeps realism, but allows a non-local guiding wave. Relational views let properties exist only relative to interactions. Collapse models introduce new dynamics. Each is a different way of saying, we can keep the predictions, but we must choose what reality means underneath. If you're honest, the real paradox isn't that the universe is irrational. It's that the universe is too consistent in a way your classical storytelling can't imitate. The correlations are not sloppy. They don't feel like ignorance. They feel like a deeper order. An order in which the particle had that value all along is not always a meaningful sentence. The world becomes less like a set of objects carrying private secrets, and more like a web of constraints that only becomes definite at contact points. There's a quiet melancholy in that, if you let it in gently. You grew up learning that reality is made of things, each with its own properties, moving through space like tiny certainties. Entanglement suggests that at the foundation, separateness is not as absolute as it feels. The boundaries between here and there remain real in practice. Your body is not smeared across the stars, but the deepest description doesn't treat isolated parts as the primary truth. It treats the relationship as primary, and that can be strangely comforting too, because it means you are not an isolated dot in a cold void. You are a pattern of interactions, a knot in the fabric of information flow, a temporary harmony of matter and memory. The same physics that refuses to give you a single classical story also tells you that connection is not an afterthought. Connection is built in, so as you breathe slowly, you can let the paradox settle into a softer question, one that doesn't demand an immediate answer. If the universe is stitched together by correlations that only become facts in the act of interaction, then what, exactly, is a fact when no one is looking? And is no one even a meaningful condition in a cosmos that never stops touching itself? Sometimes the strangest thing about quantum physics isn't the behavior of particles, it's the behavior of stories. You can take the same equations, tested, trusted, painfully precise, and tell more than one coherent narrative about what they mean. Each narrative fits the data. Each one feels calm in one place and unsettling in another. It's like having a map that never lies about distances, yet can be folded into different shapes depending on how you choose to hold it. One story says the wave function is a real physical object, and when you measure, it collapses. Not as a metaphor, an actual event. A sudden reduction of possibilities into one outcome. This makes the world feel single and sharp, the way your mind wants it to be. But it introduces a mystery. What counts as a measurement, and why should observation have special power? You end up with a theory that predicts perfectly, but leaves a seam in the fabric where collapse happens without a deeper mechanism. Another story says the wave function never collapses. The equations always apply. The universe evolves smoothly and deterministically, and what you experience as a definite outcome is simply the branch you inhabit. In that view, Schrödinger's cat is not a contradiction, it's a split. The paradox dissolves by paying a different price. You accept an enormous multiplicity of outcomes, a vast branching structure where reality is bigger than your lived line through it. The universe becomes a forest of histories, and you are one quiet path. A third kind of story says quantum states aren't physical objects in the world at all. They are states of knowledge, or beliefs, or information about expected outcomes. In that view, collapse is not a physical collapse. It's an update, like revising your map when you finally see the coastline. The paradox softens because you stop demanding that the wave function be a literal substance. But then, you face a different discomfort. If the wave function is not out there, what is? What is the world made of beneath the probabilities? And there are stories that keep realism in a more classical sense by adding hidden variables. but they often must accept non-locality, as Bell's theorem whispers. In these views, particles have definite properties guided by a wave-like structure that spans space. Nothing is random in the deepest layer, yet the guidance is non-local. A global coordination that makes classical separateness feel like a useful approximation rather than a fundamental truth. The paradox shifts from how do outcomes become real now to how does nature coordinate without signals? You can feel, underneath all these options, a shared pressure point. Quantum theory seems to resist the idea that reality is made of independent objects with complete core local properties at all times. It keeps pulling you towards something relational. What matters is not just what something is, but what it is with respect to, what it is in contact with, what information has been exchanged, what records exist, what correlations are established. This is why the paradoxes cluster around measurement. Measurement isn't a mystical act. It's a physical process where a system becomes entangled with a larger apparatus and environment, and some information becomes effectively irreversible. A record is created. A fact is born. The universe doesn't consult an observer's consciousness. It consults interaction, amplification, and the spreading of information. Yet the moment a record exists, your narrative demands. Which record? Why this one? Where did the other go? When you watch quantum physics long enough, you start to suspect that one outcome is less a primitive rule and more an emergent experience. The same way temperature emerges from many particles, even though no single particle has a temperature. The same way sound emerges from pressure waves, even though no single molecule carries a melody. Your experience of a single or continuous world may be a stable emergent layer built on deeper, more flexible rules. The paradoxes also remind you of limits that aren't just technological, but structural. Heisenberg uncertainty is not a failure of measurement devices, it's a property of the formalism. Complementarity is not a lack of cleverness, it's a statement about what can be jointly defined. Bell correlations are not a trick, they are an empirical boundary on the kind of hidden story you are allowed to tell. Quantum theory is not merely strange, it is constrained, it is consistent, it is strange in an orderly way. And sometimes, late at night, that orderliness is the most soothing part. The universe is not mocking you with chaos, it is offering you a different kind of logic, one that doesn't always allow the questions your intuition wants to ask. Which path did it really take? Might be like asking, what color is a melody? The question reveals the shape of your mind more than the shape of the world. The paradox is a mismatch between categories. If you let that mismatch be gentle, it becomes less of a threat and more of a guide. It tells you where your metaphors stop working. It tells you where language, built for rocks and rain, struggles with atoms and fields. It tells you that reality may not be a single picture, but a set of consistent rules for how experiences and records line up when systems meet. The world may not be a thing, it may be a choreography. In laboratories, the choreography is precise. A photon is prepared. A measurement basis is chosen. Detectors click. Data is filtered, corrected, and plotted. Scientists argue about error bars and systematic bias, not about mysticism. They build new devices to isolate, to entangle, to cool, to shield, to amplify. They chase coherence like a rare animal through snow. And in doing so, they keep showing that quantum mechanics is not fragile. It's the bedrock that modern technology stands on. And yet, the bedrock is translucent. You can stand on it and still see depth beneath it. Quantum paradoxes are what you notice when you look down and realize the ground you thought was solid has layers of glass and shadow. The predictions are stable. The meaning remains slippery. And maybe that slipperiness is not a failure. Maybe it's a sign that nature is deeper than the single, fixed pictures we prefer. So when you ask why quantum physics creates paradoxes, we can't explain. One calm answer is because it forces you to separate two things your mind likes to fuse. It forces you to separate the map from the territory. The description from the described, the state from the fact. It asks you to accept that facts are born in interaction, and that before interaction, the best you can have is a landscape of possibilities with lawful structure. And if you're still here, still listening, you don't need to solve the whole philosophy to take something restful from it. You can let the paradox be a lullaby of humility. The universe is understandable enough to predict, and mysterious enough to keep you gentle. You are allowed to not pin it down tonight. You are allowed to hold the questions without forcing them into one shape, because even in quantum physics, certainty is not always the point. Picture a quiet laboratory at night, the kind of place where lights are dimmed not for drama, but for focus. A small room sits inside a larger room. A sealed experiment sits inside the small room. And inside the experiment, something simple happens, a quantum measurement, a single outcome recorded by a device. Now slow your breathing, because the paradox is not about complexity. It's about layers, like dreaming inside a dream, each layer convinced it's awake. Wigner's friend is a thought experiment that asks what happens when an observer measures a quantum system inside a closed lab, and another observer outside treats the whole lab as a quantum system. The friend inside measures, say, a spin or a photon polarization, and gets a definite result. To the friend, the wave function collapses. A fact exists. A record sits in memory, in data, in the physical state of the apparatus. But Wigner, outside, who has not interacted with the lab, can in principle describe the entire lab, including the friend and the measurement device, as a superposition. That's the first moment your intuition tightens, because both descriptions seem reasonable in their own frames. The friend says, "I saw the result." Wigner says, "From my perspective, until I open the lab and correlate with your record, the lab is still in a quantum state that includes multiple outcomes. One person has a fact, the other has a superposition. Who is right?" The paradox becomes sharper when you realize this isn't just semantics. If Wigner could perform a certain kind of interference experiment on the entire lab, treating it like a giant quantum object, then, in the mathematics, he could test whether the lab remained coherent. If he sees interference, it suggests no collapse occurred from his perspective. Yet the friend inside experienced a definite outcome. The world seems to allow two incompatible stories about the same event, both grounded in the same equations. Here is where the calmest version of the question emerges. Is a measurement outcome an absolute fact of the universe, or is it a fact relative to an observer's information and interaction history? In everyday life, we treat facts as objective. A cup either shattered or it didn't. But quantum theory keeps teasing you with the possibility that facts are more like agreements between systems that have interacted, contracts signed by contact. This is not a claim that reality is subjective in the sloppy sense. The friend isn't imagining the result. The record is physical. Neurons fired, photons scattered, a measurement device changed state. The friend's reality is as real as your blanket and your pulse. The question is subtler. Can there be a consistent underlying theory in which different observers assign different quantum states to the same system, and those assignments are both correct given their information? Relational interpretations lean into this. They suggest that properties don't exist absolutely. They exist relative to interactions. The friend has interacted with the system, so the system has a definite outcome relative to the friend. Wigner has not interacted with the system lab composite, so relative to Wigner, the composite may remain in a superposition. There is no contradiction because there is no requirement for a single, observer-independent wave function that everyone must agree on at all times. Other interpretations choose different escapes. In many worlds, there is no collapse at all. The friend becomes entangled with the result, branching into versions that saw each outcome. Wigner, before opening the lab, is also part of a larger superposition. Once he opens it, he becomes correlated with one branch. The friend's definite experience is real, but it exists within a branching structure, rather than being the single global fact. The paradox shifts from who is right to how many versions exist. Collapse theories respond by saying, no, collapse is real and happens objectively, not dependent on what Wigner knows. The friend's measurement produces a physical collapse, and Wigner's external description must respect that. But then you owe the world a rule. When does collapse happen? Exactly. At what scale? By what mechanism? With what new physics? The paradox becomes an engineering challenge in the foundations of theory. And then there's another door. If you try to formalize Wigner's friend with modern quantum information tools, you run into results suggesting that certain combinations of assumptions like single outcomes, observer-independent facts, and free choice of measurement settings cannot all hold together in a consistent way. You don't have to memorize the papers to feel the pressure. The pressure is the same. Quantum theory seems to resist a single, global ledger of facts that is always the same for every observer. If that feels unsettling, let the room around you anchor you. The air is still. Your body is heavy in a way photons aren't. Decoherence keeps your world stable. For macroscopic observers like you, disagreements about facts don't happen in ordinary life because the environment forces consensus. The universe is constantly broadcasting records, light scatters, heat flows, information spreads. The friend's lab is never perfectly sealed in practice, which is why you never open a door and find your kitchen in coherent superposition. But the thought experiment is valuable because it shows the seam, the point where measurement isn't just a technical step in a calculation, but the place where your concept of reality is being negotiated. It asks whether the world is built from absolute facts or from networks of relative facts stitched together by interaction. It asks whether the wave function is a universal physical field or an information object that different observers legitimately update differently. There's a gentle kind of humility hiding in this. It's the humility of realizing that certainty might be a local phenomenon. Your facts are real, your experiences are real, but the universe may not store them in one single God's eye archive. Instead, reality might be more like a tapestry woven from many threads, each thread a record created by a particular interaction, each thread consistent where it overlaps others, and not required to become a single strand until the threads actually meet. In that sense, quantum paradoxes are not failures of the universe. They are failures of our demand for one kind of story. We want one camera angle that explains everything at once. Quantum mechanics offers something else, a set of rules that tell you what each observer can predict from where they stand, and how their predictions align when they compare notes. It's less like a single narrative and more like choreography, steps that remain lawful even when the dancers can't see the whole stage. And now, with that paradox resting softly in your hands, you can feel the emotional direction shifting. After all this strangeness, you don't need to force an answer. You can let the question dissolve into something calmer. Whatever reality is at the deepest layer, it is stable enough to let you exist, and precise enough to let us build lasers and clocks and quiet experiments that reveal its edges. And if two honest observers can carry two valid descriptions until they finally meet, then maybe I, tonight, can carry a question without resolving it, until sleep finally meets you. You've wandered through a landscape where certainty behaves differently than you were taught it should. A place where a particle can slip through a barrier it shouldn't cross, where an atom can wait an unpredictable amount of time and then change its identity in a single quiet moment, where two distant measurements can align with a precision that no local classical story can comfortably imitate. And somewhere in the middle of it all, the paradox stopped being a quirky detail and became the main character. Reality, at the smallest scales, seems to refuse a single, tidy narrative. Earlier, we watched how the quantum world offers probability not as a placeholder for ignorance, but as a fundamental ingredient. Not because nature is messy, but because nature is structured in a way that doesn't always assign definite values to things before interaction. It's a strange kind of order, like a song that only resolves into a clear melody when it reaches your ear. Until then, it's the possibility of music and carried by silent air. We met the cat in the box, not as a meme, but as a mirror. A reminder that language built for everyday objects breaks when it tries to describe systems that can hold multiple potential outcomes at once. And we saw how decoherence, this constant, invisible flood of environmental interaction, turns fragile quantum superpositions into robust, classical-looking worlds, not by choosing an outcome like a judge, but by washing away interference like wind smoothing footprints in snow. Then the story cooled into its most mathematical kind of eeriness, entanglement, Bell's theorem, the gentle brutality of an inequality that tells you the universe won't let you keep all your comforting assumptions at once. The experiments felt almost tender, detectors clicking, timing windows tightening, distances stretching, random choices made in microseconds. And the universe, again and again, returning the same answer in the language of correlations. Not chaos, not magic. Just a deeper rule set that doesn't care how badly your intuition wants the world to behave like a set of private little objects. When we stepped into Wigner's friend, the paradox turned inward. It asked what a fact even is, and whether facts can be absolute in a world where information and interaction are the gates through which reality becomes definite. It wasn't telling you that truth is subjective. It was asking something subtler, whether the universe stores reality in one single ledger, or whether reality is a network of agreements formed where systems touch and exchange information, each agreement real, each record physical, and consensus emerging not by decree but by contact. And maybe the most honest thing we learned is that quantum mechanics is not confused about its predictions. We are. The equations behave. The experiments obey. The technology works. Lasers don't hesitate. Semiconductors don't shrug. Atomic clocks don't, sort of, tick. The paradox lives in meaning, not in measurement. It lives in the gap between what the math says will happen and what our everyday language insists must already be true. So tonight, you don't have to solve it. You don't have to choose an interpretation like a team jersey. You can let the paradox be what it is, a signpost at the edge of a map, where the coastline becomes too intricate for a simple drawing. Some nights you'll lean toward collapse and a single sharp world. Some nights you'll feel the lure of branching histories. Some nights you'll find comfort in the idea that the wave function is information, an honest bookkeeping tool for expectations. And all of those moods can be held gently, without forcing your mind to pick a single final sentence. Because the deeper lesson of quantum physics is not that reality is broken. It's that reality is richer than the categories you inherited. It's that either/or is not always the right doorway at the foundation. And when you stop demanding that the universe answer in your preferred grammar, something soft happens. The paradox becomes less like a threat and more like a quiet invitation to humility, an invitation to wonder without strain. If you're still awake right now, you've probably noticed something else. Your body is still here, steady and warm, even while your mind has been traveling through impossible places. The blanket still has weight. The air still moves in and out. Your room still exists in ordinary light and shadow. Whatever is happening at the quantum level, it is happening in a way that reliably builds the world that holds you. That reliability is not trivial. It's a kind of kindness in the structure of things, and if your thoughts are still buzzing, spinning around cats, correlations, tunnels, and friends in sealed labs, let them buzz a little longer. You don't have to pin them down. You can let them drift like dust in a beam of moonlight, visible for a moment, then dissolving back into the dark. Tonight, the goal isn't to win an argument with reality, it's to let reality be vast while you become small and safe again. Thank you for giving your attention to questions that don't always come with answers. Thank you for trusting this kind of slow science, the kind that doesn't rush you, the kind that lets curiosity and rest share the same space. And if you fell asleep somewhere along the way, that's genuinely perfect. That means the paradox did its quiet job. It held your mind just long enough for your body to let go. It's strangely comforting to think that there are people listening to the same story at different hours of the night, under different skies, in different time zones, each of them holding the same questions for a while, then letting them fade. If you feel like it, leave a comment telling me where you're listening from and what time it is for you right now. And if you'd like more nights where big questions get to be gentle, you can like the video and subscribe. No pressure, just a small way to keep these late-night science stories waiting for you. Now let the room return to being just a room. Let the universe return to being far away. Your breathing can slow down without effort. Your mind doesn't have to measure anything anymore. And whatever the deepest rules are, collapse or branching, information or field, they can keep doing their quiet work while you rest, held inside a world that, paradoxically, is both mysterious and steady enough to sleep in.